Okay, by solving that equation only, that one we are getting this one. Okay, so this plot is by solving the full Poisson equation. Okay, full Poisson equation by taking electrons and the whole contribution into account. So what we did now, the symbol, so that is by solving the Poisson equation by assuming depletion. That is why you can see this kind of a linear or a sublinear kind of a relationship here. Okay, so beyond that, in accumulation and in inversion, okay, so you need to you cannot extend the depletion approximation into inversion or an accumulation, because that's wrong, and you need to solve the full Poisson equation. Okay, sometimes they are called Poisson-Boltzmann equation. That is because the relationship between charge and the potential, like it's an exponential relationship. That is why it's called Poisson-Boltzmann equation. Now let us look at one case, okay, where your surface, it's an inversion case, okay, inversion case, and you have inverted in such a way that the amount of band bending is equal to 2 times phi f. Okay, so what it says is that you have electron whole concentration here, you have electron concentration surface, these both are same. Okay, so you have inverted the surface in such a manner that the electrons concentration at the surface is same as the whole concentration at the bulk. Okay, so that voltage, okay, it has got a special name. Okay, it is known as threshold voltage. Okay, so this is threshold voltage. Okay, so you might have heard this name in transistor or something. Okay, it is like, yeah, it is normally given like the transistor turns on. Okay, so the same thing here, it comes from this one. Okay, so this is where, so it's the onset of the strong inversion. Okay, it's the onset of strong. So when psi s is greater than 2 phi f, okay, so this is, we call it a strong inverter. Okay, so you have a lot of carriers at the surface. So this voltage, okay, this voltage, okay, it's not a threshold voltage. The threshold voltage is that voltage, okay, where you have an electron concentration at the surface which is same as the majority force at the bulk. So you have completely inverted the surface, inverted the interface surface, so the electron concentration is same as the whole concentration in the bulk. So if you want, so you can extend the depletion approximation. Okay, you can, and you can see you put psi s equal to 2 phi f. Okay, here then you can see what is the depletion width at that case. Okay, so this is the depletion width. Okay, this is the depletion width here. So then you put it inside the Vg expression. Okay, this expression you put psi s equal to 2 phi f. Okay, then you get a Vg. Okay, that Vg equal to Vt. This is the threshold voltage. So we call that as a threshold. So this is the same threshold voltage. We will use this concept, or we will use this term later in the transistors also. That's the same thing. So when in a MOS capacitor or a MOS transistor, where at threshold voltage, okay, what is happening is that you are inverting the surface and you are making it rich of minority carriers. Okay, so and minority carrier concentration is same as the majority carrier concentration at the bulk. So you can calculate the threshold voltage expression. Okay, this is the same expression. Okay, so you can see this is Vs here, psi s here, this is psi s here. You put psi s equal to 2 phi f here, and in the depletion charge, so this is nothing but Q depletion over C aux, right? So this term, okay, so you apply this psi s, you put as 2 phi f here, and similarly you can do the same thing here. Okay, so only difference is that the type of the charge, that is why this sign is negative. So you can see the Vt, okay, it depends upon, okay, now let us look at the material parameters. What does Vt depends upon? Okay, one is phi f, okay, it's the amount of the band, this is also a material parameter, but then it depends upon doping, it depends upon oxide thickness. Okay, you can see, so if you are a process or device engineer, okay, so you cannot change the electron affinity of a material or something, but the doping concentrations and the oxide capacitance, because this depends upon Tox, or the thickness of the oxide. So these are under your control. So let's look at some family of curves. So this is the threshold voltage. Okay, this is the threshold voltage is plotted against this doping concentration for various oxide thicknesses. So you can see, as you vary the doping concentration from 10 to the power of 15, okay, this is 10 to the power of 15 to 10 to the power of 18, you can see what you may expect. Okay, so the threshold voltage increases. Okay, that simple, when you vary the substrate concentration, you are increasing the majority carrier concentration. Now if you are trying to invert, okay, you need to reach this concentration. You need to, so that means you require higher gate voltages. And the field. Okay, so when you vary the vary the oxide thickness, okay, what it does is that it varies the field. Okay, so for a thinner oxides, okay, it reaches faster. It reaches faster. So you can see the threshold voltage. Okay, it's smaller for thinner oxides. So this is same thing for an N-type substrate. So you keep in mind, okay, so the VT numbers, okay, the VT numbers are roughly between, like, it is between -2 to +2 or something like this one. Okay, so this is still assuming ideal case, okay, there are no other charges or something inside this one. So you have to keep this in mind in doing calculations or doing problems. Okay, so if you get a VT number something like a 10 volt or something. Okay, so you can go back and you can almost like 90% you can make sure that, okay, you have messed up your calculations. Okay, so it should be somewhere in this range. Okay, so that is why it is very important while solving problems. You should have some sense of numbers. So for example, this is a TOG, this is a doping concentration. Okay, and what's a range, right? My answer, okay, it should lie in some range. Okay, it's not like you get some 100 volt VT or something like this one. Or for same example, for electron concentration or something. Okay, suppose you get some 10 to the power of 50 or 10 to the power of 60 or something. Okay, so you can get any answer, okay, but whether it makes sense, right? That's why it's very important. As students, you should have some sense of numbers. Maybe I'll stop here. Okay, so then I will take up some questions and then we will continue in the next class. Okay, I think there is some question. Okay, so there is some question. Okay, can you discuss subthreshold current also? Okay, so I will come to that. So I think if you have seen the slides, I have put some slides on the subthreshold current also. If you think anything more is required, you can always ask questions. I can answer it. So I hope now it is clear. It's Gurpurneet. So what will be the intensity of electric field in N-type? So we have derived this now, the intensity of the electric field. Any other questions? Okay, at threshold voltage, if you further increase the gate voltage, the question is what will happen if you keep on increasing the gate voltage? So if you further increase the gate voltage, okay, so this approximation what we did, it's no longer valid. If suppose it's in strong inversion, very strong inversion, that as I said earlier, any increase in the gate voltage, when you are increasing the gate voltage, what is happening is that you are adding charges at the gate electrode. So it has to be balanced by the charges in the semiconductor. There are these electrons and holes. Okay, they can formed by generation events. So suppose you shine light, okay, a photon can generate an electron hole pair. Similarly, if you increase the temperature, okay, the electron and hole pairs can generate. And similarly, they can recombine also. So they can recombine radiatively. That means an electron and hole can recombine and emit a photon. That is what happens in LED. But in silicon, this is an indirect band gap semiconductor. So this the efficiency of that process, the electron and a hole recombining and emitting a photon, that is very, very small because of the momentum conservation involved. So what happens is that if there is a trap level inside the band gap, and if the trap level is closer to the middle of the band gap, this trap can facilitate a recombination or a generation and event. So you can visualize like first the electron gets trapped there, then it captures another hole. Okay, so then electron and the hole recombines inside the trap. So depending upon the trap numbers, okay, you can have far higher generation or recombination events that is being predicted by the thermodynamics. That is the Ni square, whatever the Ni number. So depending upon the trap concentration, you can have more generation or recombination events. For example, sometimes you utilize this one to speed up the device. Okay, so for example, in a diode or a transistor like a BJT, when it goes from on to off state, okay, so what you have to do is that you need to remove all those minority carriers from the cathode, the anode side, or from the base. Okay, so you can speed up the recombination events by selectively doping by gold or something like that. But it has also a downside. Okay, it may increase the leakage currents or something like this one. So in short, Shockley-Ritholtz is a kind of a recombination mechanism. So there is a related question: relationship between threshold voltage and leakage current. Okay, threshold voltage and leakage current. How? So threshold voltage is nothing but, okay, it's like a you are putting some number. Okay, so it's like you are calling it, okay, the transistor is on beyond threshold and off below threshold, but we will see later it's not the current goes to zero because it's a continuous process. Okay, that is why you might have heard about something known as subthreshold current. We will see later subthreshold current, there's a small current, but the subthreshold current is not there in MOS capacitor because there is no source or drain. But we will see when it comes to transistor, we can see there is a current can flow, because here there is no lateral current in a MOS capacitor because it's all M, O and S. Okay, so if there is a current, it has to flow between the gate and the semiconductor, but because the oxide is very thick, that is preventing this one. Okay, so there is no subthreshold current in a MOS capacitor, but there can be subthreshold current in a transistor. The last question is, band bending is positive impact or negative impact? I'm sorry, I didn't understand the question. Could you, you require band bending. So, the band bending, it's the heart of the field effect operation, right? So when you apply any bias at the gate, what it changes is that it changes the surface condition. It modulates the, it moves the band at the surface. Okay, so that is why you are going from accumulation, depletion, inversion and all. So you need band bending. Okay, that is band bending. Band bending only shows that there is a field present. If the bands are flat, that means in that region the field is equal to zero. So when you apply gate voltage, that means there is a field at the surface. Okay, that is why the band bending. You require band bending to modulate the carrier concentration at the surface. So what I would suggest to you before breaking is, please go through the slides. Okay, so the slides for the later, the second and the third lecture are also posted. So I think it is always good to go before that you brief, so that that will help you to understand the discussions while happening here. Okay, so there is another question: if we take two different materials for the gate oxide, is there an influence? Okay, so you mean, is it two different devices or you are mixing the gate oxide, mixing materials? So the influence of gate oxide, okay, it comes through this, okay, it comes through the COX term. Okay, the COX, okay, the COX is nothing but, so in this case it is epsilon ox by T ox. Okay, so if you change the material, what is happening is that, okay, whether the question is whether you are changing the gate insulator by fixing the T ox, or you are changing by only by changing the dielectric constant. Okay, suppose to go from SiO2 from silicon nitride or something. Okay, so then you may increase the dielectric constant from 3 to something around 7. Okay, then the question is whether you are doing at, well, what are you doing with the T ox? If you change the material by, if you increase the T ox at the same time, so that if the ratio is the same, okay, it doesn't affect the electrostatics of the transistor, because the COX is the same, because this ratio is fixed. If the TOX is different, okay, that means the COX is different, your VT could be different. Okay, the question is, okay, like combination of silicon dioxide and high K. Okay, so that's a good question, because all the modern transistors, if you buy any chip or if you buy any computer or a laptop or a cell phone, okay, it may have some combination of, okay, so the metal oxides, okay, so they have a metal here, okay, and it may have two dielectrics. Okay, so this may have a high K. Okay, so this is a epsilon 1, this is an epsilon 2, and there is a semiconductor here. Okay, so you can see this is a stacked, okay, it's a stack of dielectrics, and this epsilon 1 is greater than epsilon SiO2. Okay, so these are for various issues. For earlier I mentioned about the tunneling current, right? So that is, if the thickness is very small and the electron can tunnel from semiconductor to metal. So this is, I think these solutions are all mainly coming from to reduce the tunneling current. So if you need a, so we saw that, so if you use a high K material, you have a higher epsilon. So if you have a higher thickness, that means you are essentially the COX is the same. You can get the same performance as a silicon dioxide device, but having a thicker dielectric. Okay, so thicker dielectric, why it helps is that the tunneling probability depends only on the physical thickness, not on the electrical thickness. So it is good. It is so going to a higher dielectric materials, you can reduce the tunneling current, but having the similar COX, gate capacitance. But only thing is that then you need to appropriate change the band diagram and something, because now you have two materials. If you try to draw the energy band diagram, then you need to worry about two materials here. You need to worry about the what are the appropriate conduction band and the valence band discontinuity there. So then if you have that, you can redraw the band diagram.
Sir, what is the effect of leakage currents?
What is it?
Leakage currents.
Leakage currents, it's if you are a circuit designer, it's always bad, right? It's a leakage current, because for example, suppose if there are any leakage current, right, you are not using the device. Okay, so it's going to, suppose you are using a mobile phone or something, so that is going to drain your battery. So then the question is, where are these leakage currents coming? The origin of the leakage current, that could be from various sources. It could be tunneling, it could be your like reverse saturation current in a diode. Okay, those are all leakage current. So ideally, see, you are using all these things to make a switch, right? All these electronic devices, all these components, diodes, transistors and everything, these are like a realization of a circuit component. It's a switch. You are trying to make, whether it's a 2-terminal device or a 3-terminal device, you are trying to make switches or amplifiers. So you assume for an ideal switch, you would require if the switch is off, there shouldn't be any current to the switch, right? Now you imagine you have like billions of switches connected together, okay, but all the switches are leaky, right? So that's the same effect here. Your transistor, if it has a leakage current, that means even if you are not using your cell phone, it's kept in silent mode or something, or still there are a lot of like millions of transistors are leaking, okay, and it is draining the battery. That's the impact of the leakage current.
So in order to reduce the quantity.
Sorry, if you continue, as I said, that the MOS capacitor is being used in DRAM. Okay, for a DRAM, suppose you store a bit in a capacitor. If the leakage currents are very large, that means the charge leaks away very fast. So the DRAM, what happens is that the DRAM has to be refreshed in some couple of milliseconds. If the leakage currents are large, okay, the refresh rate in a DRAM, it has to be faster. Okay, suppose it has to refresh in like microseconds. Okay, so then you need to worry about all the architecture and everything, right? So that is why the leakage currents, okay, on a first order, leakage currents are always bad. So is there any possibility to reduce the question is there any possibility to reduce the threshold voltage required without changing the dimension? Okay, that is why. So if you look at this plot, right? So if you look at this curve, okay, this is the threshold voltage. This is the threshold voltage, this is a doping. So you can see. So this is the y-axis is the threshold voltage. So you can see, you can go back to go to lower and lower threshold voltage. For example, if you reduce the doping, the threshold voltage will be low. Similarly, if you reduce the oxide thickness, the threshold voltage will be low. So for example, you are keeping the dimension the same. I assume the dimension means the W and the L of the device, the lateral dimensions. So, but if you are varying the oxide, that means you are varying the vertical dimension, the thickness of the oxide. But if you don't want to change any dimension, that means you need to vary the doping concentration. That's the only way to adjust the threshold voltage. So there is a question: can the concentration in the inversion layer go beyond the bulk concentration if we increase the gate voltage? That's so. If it's a strongly inverted surface, the inversion layer concentration, the charge, the concentration can go beyond the bulk concentration of the whole, bulk majority carrier concentration. For example, if a very strongly inverted surface, okay, the inversion carrier concentration can go like 10 to the power of 19, close to 10 to the power of 20 or something like that, when the bulk concentration could be somewhere around 10 to the power of 16 or 10 to the power of 17. That is possible. But you can see, but the inversion layer, okay, it's not a flat layer, okay, the doping on the inversion layer carrier concentration decays, okay, it decays, it will be maximum, okay, by as far as the theory what we have seen, that it will be maximum at the interface, then it decays. Are there any more questions? I hope I have answered all the questions. I'm sorry if I have missed any. So before, let me remind you, before next week, please go through the remaining material. Okay, so you may have some extra questions, and that also we can discuss next. Okay, thank you.